Okay, there's one last thing here I want to mention about ionic chemical equations, okay, or like precipitation reaction equations. It's that when a precipitation reaction occurs, some of the ions form form the insoluble salt that falls out of the solution. That's correct. That's what we're mainly focused on. But that also does mean that there are leftover ions in solution. So we want to be able to represent this chemical equation as well. So we want to have different models, just as we have different chemical equations are models. We use different models for different purposes. So sometimes we want to focus on the leftover spectator ions, and sometimes we want to actually just focus on the solid itself. Two things, or I guess one thing really before we move forward, and I feel like this is redundant and we have said this multiple times, but all of these equations must be balanced. So please make sure that you're carrying your coefficients through with the ions, and you're triple checking that your coefficient represents the number of atoms of each kind you have. So we have three types of equations, so let's check this out. So our first type of equation is a molecular equation. So a molecular equation is what we have been looking at this whole time. All the ionic compounds are smushed together. Straightforward. In comparison, we might have a complete ionic equation, okay? So all ions that are soluble, so anything in the aqueous state is written as a separate ion, okay? So anything in the aqueous state is written as a separate ion. So we leave solids alone, and we just make sure that we're representing the total number of each kind of ion through the coefficient. So we're carrying that coefficient through. And so you can see here we went from having this AgNO3 that was together, this NaCl that was together, and this NaNO3 that was together. Those were all three in the aqueous state, so we broke them apart into their constituent ions. Silver nitrate, sodium and chlorine. Sodium and nitrate over here in the products, but we did leave that solid alone. So if it's a solid, it does not get broken apart in an ionic equation ever. So this is called the complete ionic equation. It shows every single ion broken apart as the ions hanging out. So that's the complete ionic equation. However, we may want to just kind of simplify that. So the molecular equation kind of gives us a complete look at how things are being reacted together. The complete ionic equation gives us a look into each of those individual ions and makes it clear what the ions are. However, a net ionic equation gets rid of any ions that are spectator ions. It only leaves the cation ion and the anion that form the solid precipitate in the end. So we get rid of everything else that's a spectator ion. So we see that like nitrate, it doesn't actually do anything. It hangs out as nitrate itself. Same thing, both sides. Get rid of it. Sodium, same thing. It's the same thing on both sides. It didn't do anything. It didn't really actually participate in any sort of reaction. It just did that. However, our silver and our chlorine came together to make silver chloride. So again, we get rid of all the spectator ions that do not participate in the reaction, and we only include the anion and the cation that form the precipitate itself, and then that form the precipitate and the precipitate itself. So here I just have Ag plus Cl minus makes AgCl. Okay, so we're going to go ahead and get some practice actually working through some ideas, some tips and tricks about how to determine if something is the molecular, complete, or net ionic equation. So I'm going to go ahead and take a look at the first one there on your screen. I have magnesium 2 plus 2 Cl minus gives MgCl2. So if I'm looking at this, kind of the big hint here for me is that this is likely a net ionic equation because it's so short. So remember, ionic equations and precipitation equations are double displacement. So if I'm only showing a couple of things, it's probably the net ionic because I don't really have two things to double displace here. So there's that. So this is the net ionic equation. So if I'm looking down here, I'm looking at this equation. Can I determine if this is the molecular complete or net ionic equation? I have everything smashed together, and I have 4 things. So to me, that is a huge hint that I have the molecular equation. Again, everything smashed together. I don't see any ions. If I don't see any ions, it's not going to be an ionic equation. So it can't be complete ionic or net ionic. So this is going to be the molecular equation. We also have a third equation down there. So if I'm checking this one out, it seems pretty long, it's pretty big, it's pretty spread out. We have lots and lots of different ions, and one huge hint that you have the complete ionic equation is if you can find an ion that exists on both sides. So in this case, we have 3 potassiums, and then we have, for example, nitrates the same on both sides as well. So this is going to be the complete ionic equation. And again, we're going to take a look at this last one down here. Because I don't see a whole lot, because I see only a couple of ions in a solid, I probably got the net ionic equation there. So just keep that in mind as you guys are working through this. These are just some identification tips, but we should be able to now, if we can write the molecular equation, we can break apart the ions into the complete ionic equation, and then we can also write the net ionic equation as well from that. So we're going to work through 2 examples here. We previously wrote these molecular equations when we were given the reactants and we needed to predict the products, okay? So now let's go ahead and write the molecular, complete, and net ionic equation for these guys. So if I want to write from here, I have the molecular equation. I want to write the complete ionic and the net ionic. So when I do this, what's interesting about the complete ionic equation is this. So when you write a complete ionic equation, what you have got to remember is you need to use the coefficient to represent the total number of that atom on that side of the reaction, okay? So in this case, we have calcium. However, chlorine goes from being a Cl sub 2 to pulling that from subscript up into the coefficient. So anytime we're doing this, we're going to write them as their individual ions, but the coefficient represents the total number of that ion we have. So we wouldn't write down Cl2 because remember Cl2 represents chlorine gas that's not charged at all. We don't have uncharged chlorine gas. We have aqueous chlorine ions in solution, okay? So we don't want to write Cl2 because that is not what we mean. We mean that we have 2 chloride ions, okay? And then when we look at potassium, the same thing happened, okay? Potassium had a subscript of 2. I put that 2 out in front to represent that I have 2 potassium ions. I wouldn't write K2. We would never write K2 in any scenario. It doesn't mean anything. Potassium is a 1+ ion, so we put that 2 out in front to show that we have 2 copies of that ion, okay? And then we have the sulfate ion, and we only originally had 1 copy of that. No need for a coefficient. So we have calcium sulfate here as well. So that does not receive a coefficient because it doesn't get broken apart into our ions. If it doesn't have a coefficient in the balanced equation, it's not going to have one in the complete ionic either. And then we also have potassium chloride. We see that that's aqueous, so we have to break it apart. So therefore, we end up with 2 potassiums. But also, remember that 2 doesn't just apply to the potassium ion. It also applies to the fact that we have 2 entire copies of KCl. So therefore, we have 2 potassium ions and 2 chloride ions coming from that KCl. So I have 2 potassium ions and 2 chlorine ions. So again, your coefficient in a complete ionic or net ionic equation represents the number of that ion you have in your original molecular equation. So if we want to write the net ionic equation, we look for our solid. We find the cation in our solid. we find the anion in our solid, and we get rid of anything that's a spectator ion. So if my solid is calcium sulfate, my net ionic equation will contain, that's the word I'm looking for, will contain the calcium ion and the sulfate ion. However, it's not going to contain these other ions, like the chlorine ion, that's the same on both sides. The potassium ion, that's also a spectator ion, same on both sides. So I get rid of the potassium, get rid of the chlorine. I end up with calcium plus sulfate gives me calcium sulfate. So again, we have the molecular equation. We break it apart using coefficients to show the total number of each ion we have. And then we have our net ionic equation where we're getting rid of any spectator ions. So let's do one more as an example here. So we have barium oxide and lithium sulfide. Again, those are going to make us barium sulfide and lithium oxide. So we need to write the complete ionic equation. Remember, this means we look at anything that's aqueous. We break it apart and we use a coefficient to denote the total number of that ion we have, okay? So I'm going to break the first one here, barium oxide, that's an aqueous, so I'm going to break it apart. Barium is a 2 plus, oxygen 2 minus, both of those still in the aqueous state. Neither has a subscript. I only have one barium on my left-hand side, one oxygen on my left-hand side. They get coefficients of 1. I have lithium and I have sulfide as well. So with lithium sulfide, remember we need to make sure we're showing the total number of each ion that we have. So here I have 2 lithium ions on the left-hand side, so I'm going to make sure that I put a 2 in front of the lithium ion when I break it apart. And the sulfur ion is going to be the same. So the sulfide ion here, S2 minus. So I've broken apart all of my reactants. Now I break apart anything in my products that is not a solid, that is aqueous. So barium sulfide, a solid, it stays. Lithium oxide, that's an aqueous, it gets broken apart. So I have 2 Li plus aqueous plus O2 minus aqueous. Remember, we got to make sure we're using the coefficients to show the total number of copies of that ion on that side of the equation. So this is going to be our total complete ionic equation. From there, we need to also write the net ionic equation. So if we need to write the net ionic equation, remember we get rid of any spectator ions. We make sure we have the cation ion and the anion that form the solid, and we write the solid. So in this case, barium and sulfur come together to form, or barium and sulfide come together to form barium sulfide. So I know for a fact I'm going to keep in the barium, I'm going to keep in the sulfide, I'm going to have the barium sulfide solid. However, I still had oxygen and lithium floating around before and after the reaction, so they don't count, their spectator ions. We kick them out of the net ionic equation. So these are some examples of, if you're given the molecular equation, can you write the complete and net ionic equations as well? So here's some more practice where you have the molecular equation. Can you write the complete ionic equation and the net ionic equation? I have this all written out for you so that you can check those out, get some practice in on that. And that's chapter 7. So please let me know if you have any questions. Awesome. We can write chemical equations. I'm so excited.